Cool, yeah. So glad to be here, and I found the lecture series and the course has been really great. I wish I would have taken it a while ago because I've got a lot of cool ideas to apply to my data set. It's a little bit different than what we've been talking about, but there's a lot of similarities too. But what I'm going to be doing is basically turning everything upside down, and you'll understand what I mean. Start showing you the methods and stuff. I'm going to be presenting some work I've been doing using a underwater hyperspectral imager mounted on an ROV. Yeah, so my work has been basically focusing a lot on sea ice habitats, trying to assess the impact of changing habitats, like shifting sea ice on the biophysical ecological system. And we all know that this is really important because sea ice is declining, and this is one of the most dramatic consequences of climate change. I'm sure most of you are aware of this, but just to emphasize this point, you can see the sea ice extent back the median from 1980 to 2010, and then this is from last year, about 1 year ago, how dramatic the change is, and the sea ice habitat is being lost in the summertime. But it's not just the loss of sea ice, it's the change and shift of different sea ice habitat types. And this is kind of one of the main objectives of my research right now, is to characterize these different habitat types, and then we can maybe do a better job at assessing the impact of these changing habitats in the future. So why is sea ice important? I think some of you may know this, but some of you may not even know what sea ice is. So sea ice is the frozen ocean, and it should not be mistaken for glacier ice or icebergs. I know this is a common mistake made by some people, but so sea ice, yeah, frozen ocean, so that means it's salty. Because it's salty, you get these brine channels, and you can get algae and other organisms living at the bottom of the sea ice. And actually in the Arctic and Antarctica, this is one of the most important food sources for the entire food chain. So it's the base of the food web, and it actually provides food at a really crucial time. So during winter, you don't really have much happening, no production, but right as soon as light comes out, you get a lot of algae growing at the bottom of the sea ice. And then so this feeds into the entire ecosystem. And this ice algae is acclimated to low light. So it forms before the phytoplankton bloom comes. So that's why the timing of it is so important, why it is in general so important. And as I said, I'm kind of flipping things upside down because what we've been looking at for the full week is airborne or satellite systems, where you look from the top and you are getting reflectance or reflected radiance data. Typically for sea ice sampling, to get this ice algae, you have to do one of the main standard sea ice sampling approaches is ice coring. So you take an ice core and you get this piece that has ice algae at the bottom. But I mean, it's a really excellent method, and it's been around forever. So it's something that'll continue to be essential for sea ice biophysics or sea ice biogeochemistry in general. But there are some limitations to this because you get a very small piece here, usually 9 centimeters in diameter. And depending on the temperature and the thickness of the ice, it's really demanding to go out and take a lot of ice cores. So you get a small piece of ice like this, and if the ice is 2 to 3 meters thick, then it can take you anywhere from half an hour to an hour to get this one sample. So yeah, there are some limitations to this, and you're not really getting a large coverage, right? So how representative are these samples? And this is one of the main questions that I look at. Try to improve our idea or representation of the spatial distribution of ice algae. Because if you take an ice core sample, if you want to upscale this or use it or apply the results to modeling studies, you need to know that your sample was representative of larger scale. And then you want to know how many ice core samples I need to take to get a representative sample. But there are limited ways to actually assess this. You can take images, RGB images, but you don't really get a good idea of the algae because it's not so easily to see in most cases. Here you can see it because this is above the ice, right? So you get light, but when you're below the ice, there's a lot less light. So our eyes aren't good at seeing these things, but if you use the full spectrum, then you can get at a lot more information. So that's what I'm going to be presenting now. So this actually, believe it or not, is the very first study that has used a UHI mounted on an ROV to image sea ice. The UHI there were some other studies done in Antarctica, but they used like a sled towed underneath the ice, and those were the two initial UHI studies on sea ice, and they're really good papers. So I recommend reading them, and a lot of the stuff that I would like to do apply some of their methods to the stuff I'm doing. But the ROV kind of has a little bit greater reach, so you can get a more larger scale view of the ice. But it wasn't without challenges in itself. So yeah, and I'll go through that because it was the first one. I mean, I'm not a pro or an expert in integrating UHI systems to ROVs, but we had a good team, so we were able to manage to do it. So, and as I said, the objective or the main goal of my research is to look at different ice habitats. And as I showed in some other slides, or as you may have seen from pictures, you may get an idea of what sea ice looks like from above. And sometimes it's just, it's just a flat sheet of ice, and a lot of the ice around Svalbard is actually just flat landfast ice. And so this is quite uniform. But throughout the entire Arctic, you have a lot of different sea ice habitats. And the one that's least studied is called sea ice ridges. And there were a couple studies done, one by myself and another by Mar Fernandez-Mendez, that found that ridges actually are hotspots, biological hotspots. And there were some other previous studies from a while, a couple decades ago that found some indication of this as well. But the reason why is because you have these blocks that pile up because the ice is mobile, it's dynamic, it's shifting and crashing into each other. So the blocks pile up and you get these pore spaces in here. And then on the top, you don't get as much snow. So you get a really good habitat and a lot of space for algae to grow, fish to swim around in and shelter, copepods, other zooplankton living in these pore spaces. So now thinking of this as a unique habitat, and how do we sample this? So yeah, you can use standard ice coring techniques. You can go in and maybe get some of the water within here. The problem with ice coring and doing this is that you actually destroy the area. So to do temporal studies, it's difficult. And then if you think back to what I said about the limitations of ice coring, taking one ice core from a ridge is definitely over an hour to take one sample. So then this brought me to the idea to use novel or advanced technologies such as the hyperspectral imagery, because you can get a lot of information about what's happening at the bottom of these ridges, just based on those images. So then I put in a proposal to buy one of these cameras, and I bought it, and it arrived actually one day before I went on the expedition, and that was because of the coronavirus. So I got it shipped to my institute, and then I left the next day, and then we had to integrate it on the ship. In the middle of the coronavirus, it was hard to get anything, so I didn't have the right cables, but we had a cable on the ship that I was pretty sure was the right one half of the cable, and then I ordered another half of the cables, and then we had to do a lot of electrical engineering and integration on the ship. And so the expedition that I was involved in is called MOSAIC. I'm sure some of you have heard of this. It's one of the largest Arctic research expeditions ever conducted, and I was really fortunate to be involved. So the Pelaston, it's a German research icebreaker, froze into the ice. So it left from Tromsø actually, came through the Røysen Basin, and then it was frozen in the ice here, and it drifted all the way, over a period of from, when was it, end of September, October till the end of my leg was August in the Fram Strait. And so what I'm going to be presenting about is the time that the Pelasgian was here. So this is where I got on the ship, right here, where we started on the ice floe, and then it drifted down through into the Fram Strait. And while I was on the ice floe, this is what it looked like. So here's the Pelasgian here, and this was our main ice floe. So this is where most of the research was being done. And as you can see, it's quite heterogeneous. You have a lot of melt ponds forming. There's snow in some places, no snow in other places. So you can imagine what it's like underneath there too. Here's the system. It's an ecotone UHI Ocean Vision 2000, which means that it can go down to 2,000 meters, but that's not necessary because we just go under the ice to maybe 10 meters depth. Has a spectral range of 380 to 720 nanometers and a spectral resolution of around 2.5 nanometers. And so here's a picture, what I was telling you about. I had one half of the cable here and then the other half of the cable on the ship. So we had to splice it and do underwater cable manufacturing on the ship and then integrating it into the ROV system. Wasn't straightforward, but we managed to do it. And then we mounted it onto the ROV. The ROV is called the Beast. And this is where it is here. And the cool thing that we actually had right beside it, which will be helpful later on, and I haven't been able to process this yet, but this is a multi-beam sonar. So it would be kind of like a LiDAR or something. And it has the same field of view as the UHI, and it's basically right beside it. So then combining those two data sets would be really important to see the distribution based on the bottom ice topography. And I'll show some more figures about this data later on. And this is it going through the hole. So yeah, and coming back to the logistical aspects a little bit, because when you work with sea ice and you want to get underneath the ice, it's very difficult. So you have to make these big holes. And then of course, this takes a lot of time. So depending on the ice thickness, you can take between 4 and 8 or 12 hours to make a hole like this. So you need to have quite a bit of time on these flows to be able to set up such infrastructure. But we had several months there, so we were lucky. And there's the UHI again here, and there's the multi-beam sonar right beside it. So here are some images, what it looks like under the ice. Not great images because the light's not usually the best, but you have large blocks coming through. The variability is really high in the light field. So this is quite, it makes things a little bit more complicated when you start looking at the data, but also to navigate. And also when you come back to the ice scoring, okay, when you take ice scores, how representative of the area is it? Because if it's so variable, then how do you represent that with just one sample or two samples? So that's why the hyperspectral imagery is so important, I think, for these studies, and it's basically the same as airborne hyperspectral imagery. Before that, there was a lot of other types of remote sensing and sampling, but then the advancements you can make with knowing how things vary at larger spatial scales is really important. So I guess the key difference here between the two methods or the two approaches is that with the airborne stuff, you're looking at the reflected light. So light comes in, hits the snow or ice surface, reflects off, and if you're measuring from the surface, you get the reflected irradiance. But here we get the transmitted radiance. So the light comes through the ice, it gets affected by the snow and the ice and the algae, and then we see the radiance underneath, the transmitted radiance. So it's difficult, it has this added, maybe a little bit, an added component to the spectra, where this influence on the spectra is highly variable up here, and there's no way to really measure that influence. You can, but that's just an added level of logistical effort that you need to go and measure all the snow and ice properties. in the entire area, which is very difficult. But then coming back to one of the key advantages of this system is that you can do it non-destructively. So if you want to repeat the same site, you don't want to destroy it or go there and measure anything. You want to keep it pristine. So then identifying the variability of the snow or the ice properties is difficult. And that's one challenge for the future advancements of underwater hyperspectral imagery, really, is to really get at how the snow and ice is affecting the spectra, just in the same way as you do atmospheric correction, I guess. But the thing is the snow and ice is highly variable in comparison to the atmosphere. So making those corrections will be a challenge, but something that I'll be looking into, and I'm sure other groups will be as well. So the main objective, as I said, was to characterize different habitats. So what we did is we did surveys along the flank of the ridge. So trying to characterize the ridge itself. We didn't do the bottom of the ridge because it's really quite dark underneath there, about 7-8 meters of ice. So you can't really see. And the other thing is that if you go down here, you can get tangled in the blocks with the ROV, and then you would lose the ROV. So it was a risk that we didn't really want to take. So we had 2 survey sites, one along the flank of the ridge and one on level ice. And then what we can do from that is compare the 2 different habitats, and that's what I'm going to get into now. But as I was mentioning before, is that on sea ice, you have this reflectance, or the reflected light, which is most of the light actually gets reflected from the snow and ice surface, as you know from other hyperspectral data. But then some of it is absorbed or scattered, and then the rest is transmitted. So you get a very small percentage of this. The point here, though, is that it's highly variable on the ice, depending on melt ponds, thickness of the ice, snow cover, and the ice type as well. So first-year ice or multi-year ice, these types of things. And then, as I alluded to before, the spectral extinction of the light going through the ice is highly variable, and it's not necessarily flat. So you have it influencing the spectra differently along the spectrum, but also between different sites. So depending on how thick the snow is, what type of snow it is, what type of ice it is, these things affect the spectra. And as I said before, you don't really have this information to then go back and correct for that effect on the spectrum. So one level of complexity there that we need to just to remember when you start looking at the spectrum. So here is the flow. I showed you this picture already. This is a surface elevation model. So this was done by an airborne laser scanner, and this is the view from here. This picture, sorry, is a view coming from this direction. There's the ship, and here is the study location that I'm going to be talking about now. So you can see this bright spot here. This is a ridge, and this is called Yaridge. It was named after my son, Yari. And this is the other level ice area that we surveyed. And I hope you can see this on my screen. It doesn't look so great, but this is a bottom ice topography map, so sea ice draft. And this is created from the multi-beam sonar. This is from the same day as these surveys were done. So here you can see the ridge. And this is a lot thicker ice. It's not as variable here as on the ridge heel. This is the thickest part of the ridge, but it's still 2 to 4 meters. I think I have that here. Yeah. So this ice here is between 2 to 4 meters. This distance of the survey is about 64 meters. And now the level ice is about 59 meter survey, and it's below 2 meters of thickness. So we do have 2 different habitat types that we surveyed on this date. And these are what the surveys that I'm going to be looking at in more detail from a hyperspectral point of view. So here is a subset from these 2 surveys. You can see the variability. One obvious thing here is that along the edges, there's no good data. So I will have removed that in further analysis. One obvious thing is that in general, this has a higher transmitted radiance. So that's what this is called, the amount of radiance that is transmitted through the ice. In general, than the ridge flank, and this is expected because the ice is thicker and there's more snow. But the key thing here is just the variability, and this is something that we don't have any information about for the bottom ice environment, because this is one of the first, this was actually the first survey done in Arctic ice. But we don't have these types of observations for Arctic sea ice. So getting this really small microscale variability is pretty unique. So now I'm going to just go through some of the methods that I've used and some of the software tools I've used. So everything that I'm going to show is open access, freely available. I used Python and some of the toolboxes within Python and QGIS. However, after seeing all the cool things you can do with MV, maybe I should have started with MV, but I find that using programming or scripting, you really get to know your method a lot better. You have to dig deeper into actually what's going on and get a better understanding, because if you use standard packages that have already been developed, you can just push buttons and then get output, and you should really understand what you're doing. I guess, yeah. So that's one reason why I said that I did it this way, but it was probably just because I didn't know the other methods at the time. So yeah, I'm gonna go through some of the tools I used. So PCA, reducing the dimensionality. This is something that we looked at, I think, in all of the hands-on sessions. This, I'm going to be using the machine learning algorithm called support vector machine, and I think this is also available in MV. I saw it there, I'm pretty sure. And using some supervised classification, we can do machine learning classification, create a model, and then apply that to the entire data set. So first, here are just some example of some Python script that I used or developed for loading in the data, doing some processing, plotting the data, just exploring it. And the one thing too is, well, because hyperspectral data is so large, the camera or the imager actually subsets it into smaller pieces of more manageable data. And then also in Python, it has some limitations on the size of data you can import. So then my first kind of challenge was to figure out how big of an image I can work with without crashing my computer, or having Python stop, and then adding these subsets together and then processing. So if you just have one image, then maybe NV is a good approach. But if you have multiple images and you need to do processing on the large data sets, making scripts has the advantage that you can repeat the same thing over and over again, or you can do it or apply it on many images. So that's another advantage of the Python scripting. And then it outputs these figures. And one thing I always do is I just plot the dimensions of the data set, because yeah, when you're actually working with 3-dimensional or 4-dimensional data, you have to identify the dimensions when you process things. So to maintain the dimensions is really important, and that's just one check that I do. And maybe others have other methods or approaches to do this, but it just reminds me or kind of confirms that I'm doing, the data are still in the right format or the right orientation. Yeah. So next, this just goes through the principal component analysis. So it goes through the data and it outputs, does this calculation, which takes some time. And maybe you remember some of the figures that output from the PCA analysis. And this one, I think it's just upside down in comparison to the figure that we had in NV. And then it outputs the different bands or the different PCs. They're just called bands here. But then again, yeah, you can go through the different bands and see at what point it becomes noisy, just as we did in MV. But here you can see I just plotted the first 8 bands. Oh yeah, here. You can see that at some point, you do see here it starts to get noisy, maybe a little bit of speckle here. But yeah, within this machine learning algorithm support vector machine, I think it takes this into account, and then it combines the different PCs. but that's a later step. So then this step, I'm coming into QGIS to do this more manual supervised classification. And that, I guess, is one disadvantage of Python, is that it doesn't have a user interface GUI type thing. So you have to script everything, and you can't just go in and point and click and select and that kind of stuff with your data. So I brought the images in. I was using MV format, so you can just output your data into MV format. And then I create an RGB composite just as we display them in MV. And then I also created a raster, just an empty raster that has to be the same dimension as your image. And then I classify different regions. So as you can see here, this is algae. So this is, to remind you, this is looking upwards at the bottom of the sea ice. So this is transmitted light that you're seeing through the ice. And you can see the algae. It's quite obvious where the algae are, strands of Melisera. And so I can come in here and I can look at where the algae is. I can identify those regions as algae. And then I can look at uniform regions where I don't see any algae and classify those. So this is just creating these supervision classes, or the regions of interest, to then put into your algorithm. And this tool here, so you have QGIS, and one of the tools that I'm using here is called Serval. It looks like this, and you just have to learn how to do that. It's quite easy if you're used to GIS software. And then you assign the different values. So you can do this with multiple different classes. Yeah, but you just have to be able to identify the different regions, I guess. That's the same for any hyperspectral data. And then I think I posted this already in the chat when we were talking about different packages of hyperspectral image analysis. So this is something that has a lot of the same tools, I guess, as AMD. Maybe it's not as powerful, but it's a toolbox that was just released in June or July this year. It's called AVHYAS, and here are some links that you can go to learn about it. It has really good documentation, lots of cool things. I haven't gone into this because I did most of my processing already before this came out. I may go back and look at this, but I'll probably start with MV as my next steps. Yeah, but just an example of a free open software that you can use. So here, just some examples of how I classified these images. So this is one of the full surveys, and you can go through and you can see these algae aggregates, different areas and places where there is. And actually, sorry, the color scheme here is backwards. So the red in this one is actually algae, and the green is not algae. It's confusing, but yeah. So just examples of how I went through it and classified the different regions. And then now I would bring this back into Python, so this classified area. And then what I can do is just extract the spectra from the algae. So this is algae spectra, and then this is no algae spectra. And that's basically what you would expect and what I was hoping to see. And there's one step here that I forgot to mention. Because of all the snow and ice and influence, and the magnitude is so variable, the transmitted radiance, what I wanted to do is basically just look at the shape of the spectra. So one thing that you can do is called standardizing the spectra. And what this, it essentially just removes the magnitude. So it keeps the shape, but it removes the magnitude. And I may have an example later on showing, why this is important, but then you can just see here that within the no algae, you have, even if the magnitude was different, you can just compare the shapes of the curves, and it's easy to see where the variability is, right? And here, you have variability in here, and variability in here. So that's where the algae is absorbing or influencing the spectra in these two regions. So if you had the magnitude, if you just had the raw radiance spectra, then this type of thing is a lot more difficult to identify. And then also within the PCA analysis, then most of your variability is coming from the magnitude of the light. So this makes it a bit more powerful, in my opinion. and then just averaging the spectra to see, yeah, the differences, and this is what you get. So again, just plotting this all together, you have the no algae, algae, the mean, and there should be error bars or standard deviation on these, but I don't think you can see them. And then the difference between the spectra here. So then you can just look at this and see where the variability is, where the algae is influencing the spectra. And this is important to know because then you can develop maybe further algorithms or other, or you can, maybe it helps you identify which other methods you can use. So at first, I'm just using this support machine algorithm, which does a lot of the work for me. But I would like to come back and use some other methods and compare the difference. So after you have the different algae and no algae regions, you plug this into your model, and it creates the support vector model, or sorry, the support vector machine creates a model, and then it does some cross-validation and training, and you get this model assessment where this block here and this block here are the correct identification of algae and no algae layers. And then here is the incorrect identification of the different classes. So you can see that it does very well in the classification, and here as well. These are just different surveys. And then you get that model once you have evaluated it, how well it is, and then you can apply this predictive model to your entire data set. And so you get this model output. What I've done here is identified areas where there's no algae as black and where there's algae as green. So a summary of what I have done. So you first do dimensionality reduction with PCA, you do your ground truthing, and you combine this to create this model using whatever algorithm you have. You can use others as well. I just picked this one. And then you get the model output. And then what you can do is then bring this back into QGIS and just look at how your model is actually doing on your data set. So here you can see the algae layers, and this habitat classification, 0 and 1. So 0 is no algae, 1 is algae, is shown here as an overlay. So you can see that it does quite a good job at identifying the algae regions when you compare the two. So just another step that you can use QGIS for, to then look at manually, look through the images and overlay data. So it's nice to be able to investigate that a little bit more in detail. So now coming back to the more scientific aspects of it. So as I said, one of the main objectives of my research is to characterize and compare different habitats. So we have one habitat here, which is the ridge flank. And then we have the level ice. So when we do the habitat classification for both of these, you get quite different. Maybe the patterns are similar, but this has about 8.5% algae habitat, and this has about 36% algae habitat. So this is a unique finding. Or maybe not so unique, but yeah, I guess it's important is what I meant to say. Maybe somehow could be expected because, well, we found higher biomass in algae, or higher algae biomass in ridges before. But one of the reasons for this, or one of the hypotheses that we're working on, is that the reason why this is happening, and this is in the middle of summer, so melt season, right? This is thicker ice. So it has higher snow on top, so then it's insulated from the melt, and it's thicker, so it melts slower. So the hypothesis is that there's more algae here because it's melting slower. And here, as the ice melts, this actually releases the algae. So if there's like a threshold melt rate, that if it's a higher melt rate than a certain point, then the algae can't stay attached to the ice anymore. So that's the working hypothesis at the moment. And this is just one survey, but we do have a time series of these data we have 5 surveys over a full month, as well as the bottom ice topography data. So we can look at melt rates and combine that with UHI surveys to get a better idea of how that community is changing. And the other thing that I want to look at is also maybe looking at the variability of the spectra of algae communities. So seeing if there's any stress that we can identify, or you know, a change in pigment signature, something like this. These are all unique things that have never been done before for sea ice algae. So there's no shortage of ideas or things to look at within this data. And to come back to this methodological approaches, ice coring is a prime example, because as I mentioned, you know, it's important to understand if your samples are representative of the region, so that you can, you know, say something about the larger area. So one of the main things that we did on this expedition is we identified coring sites, and we tried to best represent each location by taking 20 to 30 ice cores in about a 10 by 10 meter area, and then moving over, you know, 5 meters beside it the next week and doing the same thing. So you get maybe a temporal, I'm trying to address the spatial temporal variability of the sea ice biogeochemistry. But so I just wanted to highlight this here with these data. You can see, for example, if you had these 10 by 10 meter blocks, so in the, let's call this the y-axis, is about let's say 60 meters. So then you do have maybe 10 meters in this direction. The x direction is not to scale. But if you took ice cores from this region, for example, 9 ice cores, and you said this was representative of this region, and maybe the larger region. And then the next week you came back and you did this region, and then so on and so forth for each week. You couldn't really, based on this distribution of algae, you would not be able to say anything about the spatial or the temporal aspect, because the between site variability is very large. So you're not representing it spatially. And so then you can't really address any of the temporal aspect, because that variability between the sites is not due to the temporal aspect, but rather the spatial aspect. And the same with this site. So I guess this just emphasizes the need to use this hyperspectral imagery data combined with the ice coring data to really get at, you know, how represented are my samples and how we can maybe upscale that and get and then apply this to models and so forth. So yeah, I guess the point is, do we capture this? And with ice coring, I would say no, not at this time. Maybe sooner, when the algae distribution is perhaps a bit more uniform. But we don't have surveys for earlier than this, so unfortunately. And yeah, as I already kind of mentioned, we do have a time series for you know, several surveys over the month of July. So we have 5 different time points where we have UHS surveys for the same regions. And we also have this multi-beam sonar topography maps showing the draft. So this is where the bottom of the ice is. And then you can assess the bottom ice, you know, how the geometry is. Maybe this influences where the algae are or the melt rates. And this is the main hypothesis, is that it's mostly controlled by the melt. So the next steps, and one of the more important things I think, is to really get at the biomass. So you can get the distribution, and that's important in itself, but now we want to get some indication of how much algae is there. And it's not necessarily needed to get an actual you know, chlorophyll biomass or milligrams of chlorophyll per meter squared or something like this. But I think getting at even just relative biomass so you can compare the two regions is sufficient. And my first step was to look at basically a transect across an algae patch. So assuming that as you move across the algae patch, you would go from lower biomass into higher biomass, and there would be some kind of gradient. So then we can look at the spectra and see if that's the case within the spectra. And within those regions that we do see the variability, is it primarily driven by biomass? And so here's the standardized spectra that I was already talking about. And as you go from this point to the middle, so yellow to green, as an indication of maybe low biomass to high biomass, you can see that indeed it's going from, you know, low biomass to high biomass, and there's variability in here. That's a gradient. And the same with this part of the spectrum. And then as we go, you yeah, from the middle out, that's this side here, you have the same pattern. So this is a good indication that we can use these two regions of the spectra and the variability in here. Perhaps I would only assume that we could just do like in a linear way to get at the relative biomass proxy for algae. And this here is exactly what I was talking about before. So this is the radiance, transmitted radiance values, unstandardized, and this is the standardized. So as you look at this, you can't really see that variability as well because it's not showing you the shape, but it's mostly showing you the magnitude and where these peaks are. So once you standardize it, you can really see where that variability is within the spectra. And then, yeah, so I think one approach that I would like to try next is using some spectral mixture analysis, and then you can just do percentage algae. So if you find a location, for example, as your algae patch or algae spectrum, such as here, somewhere where that's really dark and what you think is almost 100% algae, and then somewhere that's zero algae, you can maybe get a percent algae spectral mixture analysis as a proxy for biomass. This is my first idea, and that's something that I'll try out and see how the results look. So here's a summary. So this is the ridge that we were surveying under, called the ridge, and it looks exactly like Polaria. If you've ever been to Tromsø, this is the Polaria aquarium / museum place. So it's quite cool that it looked exactly like what it's supposed to look like, actually, sea ice blocks. And I'm not going to go too much into this, but these are the two studies that I was talking about that have introduced the UHI system for sea ice in Antarctica by Emiliano Smoli. He's in Tasmania at the same institute Laura's at, and she's probably here listening. And she'll probably be working on UHI stuff as well. And as I said, yeah, this is the first the results from the UHI mounted on an ROV for sea ice work. It's a really good non-destructive observational system. And it should be complemented with ice coring, not to replace it, but it's a good complement to get at the spatial temporal analysis. And then I showed you the first comparison of the ice types that we used, and we can continue to look at the differences between these ice types over time and get an indication of perhaps how these habitats will shift in the future, because this is something that we can model and predict much better than ecosystem is the sea ice. I wouldn't say that we can predict how the sea ice is going to act really good, but we can have some better predictions of the physical aspects in comparison to the ecological aspects, in my opinion. Yeah, and then as I just mentioned, I found I have quite a lot of ideas that I learned through this course, so it's been really nice to be involved and see all the presentations and all the hands-on stuff. So applying some of these methods in NV, as I said, the spectral mixture analysis to get some indication of relative algae biomass.